Hello. So today we'll be going over this problem here. And so this is going to be a probability question. So in general, with probability questions, how I like approaching them is first figuring out what are the givens in my problem, and then we can know like what kind of method to use. For example, do we want to use discrete probability or do we want to use Bayes or something like that? So first, let's identify some of the variables we have in this question. So first we have he's late. So let's say if Brian is late, we'll let that be L, and that's like if he's late. And then he can take three sorts of buses: Commuter North, Bursley Baits, or Northwood Express. So I'm just going to denote those CN, BB, and NE. Then in this question, we're given if he takes Commuter North, there's a 50% chance he's late. So this is a conditional probability. So the probability that he is late given he takes Commuter North is equal to 0.5. Then after that, we also have the probability that he is late given he takes Bursley Baits is 0.2. And then we also have the probability that he is late given he takes Northwood Express is 0.05. We also know that he takes Commuter North 30% of the time, Bursley Baits 10%, and Northwood Express 60% of the time. So we know that P of CN equals 0.3, P of BB equals 0.1, and P of NE equals 0.6. So now from these probabilities that are given, we know we have some conditional things, and we know that we want to find the probability that Brian was not late to class. Given that Brian was not late to class, what is the probability he took Commuter North? So we want to find P of C given that he was not late. So I will complement. So in this question, generally we see that we have conditional probabilities here, and we have a good amount of them. And we know like the probabilities of him taking the buses. So generally when we see something like that, we would think of using the Bayes theorem. Oops. To take a step back first, Bayes' theorem relates a lot to conditional probability. So in this case, for example, we have these three types of ways he can get to class. He can either take Commuter North, Bursley Baits, or the Northwood Express. And if you notice, the probabilities here are 0.3, 0.1, and 0.6. These here will add up to equal to 1. So what we can do is we can take this sample space of him, how he's getting to class, and we can partition it up so that like maybe this chunk is like him taking Commuter North, this chunk is him taking Bursley Baits, and then this final chunk is him taking the Northwood Express. So now that we partition it into chunks, what we can look at is, well, you can think of him like he can either be late or he can like be on time. And so you can think of then partitioning these three pieces into him being late or on time. So maybe, I don't know, maybe there's some like divide like that. I don't know if the percentages are right, but like on this side is like he's late, and then this side is he's not late. Late, not late, late, and not late. So then from here, like what we can do is we can think of the denominator of the Bayes theorem. So if we're trying to find the probability that Brian is not late, what this equals to, if we look at this partitioning here, it's just equal to the probability of him taking Commuter North and being not late, like this piece here, and then plus the probability of him taking Bursley Baits and being not late, so this chunk here, and then finally also the piece where he takes Northwood Express and is not late, so this piece here. So if we can see clearly, like this is using the law of total probability, and we can get this entire chunk of him being not late based off of the other pieces. So this is kind of how that would relate to the Bayes theorem. So this here, if we write it out just as conditional probability, this would be equal to probability of, oh, this was supposed to be Commuter North. I forgot the N. So probability of Commuter North and him not being late divided by the probability of him not being late. So this is by the definition of conditional probability, we get this. Now what we can do is we can take what we just learned and we can apply that to this problem. So we have probability of Commuter North and not being late divided by, we take the PL and we plug in, or P of L complement, and we plug in this whole chunk. So P of Cn and L complement plus P of BB and L complement plus P of NE and L complement. So we get this here. So that's kind of how we move forward, kind of this is explaining how the Bayes theorem comes about, and not just starting directly at Bayes. It's looking at how Bayes relates to conditional probability. So then after that, now this is kind of where our Bayes theorem comes out of. So the probability of Cn and L complement, well, what is this? So what we can do here is we can say that using conditional probability, that this equals the probability of L complement given Cn times the probability of Cn. And so how this relates to conditional probability, we can think about dividing both sides by probability of Cn, and we would get probability of Cn and L complement over probability of Cn equals probability of L complement given Cn, which gives us back the conditional probability formula. So that's what's happening. So like to understand Bayes better, kind of that's what's happening under the hood, and that's how we get to the Bayes theorem. So from here, we can say that this is equal to the probability of L complement given Cn times probability of Cn, and then we can split each of those bottom ones up in the same way. So we would have L complement given Cn times probability of Cn plus probability of L complement given BB times probability of BB, and then plus probability of L complement given Northwood Express times probability of Northwood Express. So after this, we can take what we have with the givens here and plug that in. So we have P of L complement given Cn. So here we have P of L given Cn. So actually it's the case, same with this like disjoint and like partitioning kind of thing. We know that P of L given Cn plus P of L complement given Cn, this is going to be equal to 1. So we just take 1 minus that, 1 minus this value. So P of L complement given Cn is 0.5. And then P of Cn was the 0.3 from before. and then we divide by L complement given Cn times PCn, which is the same thing as the top, so 0.5 times 0.3 plus L complement given BB, so we have L given BB, so L complement given BB would be 0.8, and then times probability of taking BB is 0.1, and then we add on P of L complement given NE, so that would be 0.95, and then times P of NE would be 0.6 here. So this would be our final conclusion. And notice how we kind of moved. So in general, you might probably start with the Bayes theorem here. So this is the Bayes theorem, but this is just to help you guys understand how conditional probability and the Bayes theorem relate together. So we started off with our conditional form, and we move about using, in this step, we use something called the law of total probability. And then we move forward and we finally arrive at this form of the Bayes theorem. And notice one thing that I mentioned at the beginning, these bottom pieces have to sum up to equal to 1. So this thing you're multiplying by here, this like there's 3 here, sometimes you'll see 2, sometimes you'll see more than that, but notice that those values all have to sum up to 1, and this is because you need these events. So in this case, taking Commuter North, taking Bursley Baits, and taking Northwood Express, you need this to partition out the entire sample space. So the probability of the entire sample space is going to be equal to 1. So that's why you have to add up. When you add up these pieces, you will get 1. So yeah, so that's like what happened there with the Cn, BB, and NE. These, when you kind of put them together, this is going to be equal to your sample space. So yeah, hopefully that kind of helps clarify like the relationship between Bayes' theorem and conditional probability and how we move forward. This is important here to notice that this bottom part is just actually equal to P of L complement from conditional probability. And so based on certain problems, you might be starting out just with the conditional probability form. In other problems, you might want to use the Bayes form. So this kind of determining what you're given and what you want to achieve, this helps you determine, do I want to use the conditional probability form or do I want to use the Bayes probability form? So thank you guys for listening to this and have a wonderful day.